So we arrived at the point that we know what is the pressure, that it's in terms of the density, and we also know that it depends on the speed, the average speed square. But now we want to have actually a molecular interpretation of something that is very close to us, which is the temperature. So I'm going to start from where we left, so where I have the pressure. So the pressure, it's a third times N times M divided by L cubed. So I have the volume actually times V bar squared. So let me actually rewrite it with volume here. Actually, let me say that this is the volume, right? And let's multiply to the left and to the right by the volume. So I have PV equal N divided by 3 times M times the average speed square. Now I'm going to do some algebraic steps in order for me to have the kinetic energy on the right. Why the kinetic energy? Well, because I can see I already have the mass and I already have the average speed square of the molecules, and therefore it's very useful to me to relate the average kinetic energy of the molecule. So in order to have the kinetic energy, I just have to multiply by half here and here, and then I have to move these 3 to the left hand side. So let me say that this becomes 3 divided by 2 times PV, then this is equal to N times, and then half mv bar squared. Now this one is the average kinetic energy of one particle, right? And this is the number of particles that I have in my box, and therefore this is going to be somehow the total kinetic energy that I have in the box. I also know that for an ideal gas, P times V, it's actually equal to nR and the temperature. So I can actually rewrite P times V as N times R times T. So let me do it here. So I have 3 divided by 2 times, and then N times R times T, and this is going to be equal to N times half mv bar squared. What it's exactly giving me this? Well, let's re-express the number of moles as the number of atoms or number of particles divided by the Avogadro number. In this case, you see that we're going to have 3.5 times N divided by Na times R times T equal N times half mv bar squared. And now capital N, which is the number of the particle, can actually be cancelled out. And therefore I have that the kinetic energy of the singular molecule can be expressed as 3.5 R divided by Na times the temperature. So first of all, the thing that I recognize is that the temperature, clearly it's related to the kinetic energy of the singular particle, okay? So temperature is proportional to the kinetic energy on average of each particle. And second of all, actually there is a constant that it's appearing, which is R divided by the Avogadro number, which actually takes the name of the Boltzmann constant, so Kb, Boltzmann. And this constant, okay, if you calculate it, actually it's equal to 1.38 times 10 to the minus 23 joules per Kelvin. But what does it tell us exactly this? Well, in reality, it tells us a lot. So it tells us actually that the kinetic energy, it's equal, so the mean kinetic energy, it's equal to 3 times kBT divided by 2. Now, why 3 times? Well, this 3 actually is not casual after all. It depends on the dimension that we are considering. We are in 3D, in 3 dimension, and therefore for each direction where we can have a kinetic energy in the X, in the Y, and in the Z, we're going to have a half kBt of energy available. This number actually, it's very important. This factor in front is very important because it relates to the degrees of freedom, they are called, degrees of freedom of the molecules. And in this case, we're just studying molecules that can move to the X direction, in the Y direction, in the Z direction. But let's assume that they are molecules with some symmetries and rotational movement and so on. Well, this number will increase because the degrees of freedom, so the freedom of moving in different directions, plus the rotational symmetries of the system, are going to give a higher number of degrees of freedom, and therefore the kinetic energy could be higher in principle. Yes. So what we discover, what is really the important message here, is that the temperature depends on the mean or average kinetic energy. And this is something that you must remember because it's appearing even in multiple choice question. Okay? So the kinetic theory of gas is linked to the temperature, which is a macroscopic quantity. It's something that we can measure outside with a thermometer, basically, to the microscopic energy of each molecule in the gas.